Deep in the heart of our galaxy, 4 million miles from where you're sitting right now, something so massive and so violent exists that it bends space and time around itself like putty. Light itself cannot escape its grip. Matter spiraling toward it heats to billions of degrees before vanishing forever across an invisible boundary called the event horizon. This is Sagittarius A star, our galaxy's supermassive black hole. But what if I told you that everything you think you know about where you are in the universe is wrong? What if our entire cosmos, every star, every planet, every atom in your body, exists not in some vast expanding space, but inside something far more impossible? Today we're diving into one of the most mind-bending theories in modern physics. Evidence is mounting that our universe might not be what it appears. Scientists are discovering mathematical relationships, observational data, and theoretical frameworks that point toward a conclusion so radical it challenges everything we understand about reality itself. The numbers don't lie, and they're telling us a story that will fundamentally change how you see your place in existence. Like and subscribe, because we're about to explore evidence suggesting that our entire universe could be the interior of a colossal black hole, and the implications will shake you to your core. Prepare yourselves. We begin. Picture the moment of the Big Bang. 13.8 billion years ago, everything that exists today was compressed into a point smaller than the period at the end of this sentence. All matter, all energy, all space, all time, crushed together in a singularity of infinite density and infinite temperature. Then, in an instant that defies comprehension, it exploded outward, creating space as it expanded, cooling and stretching, until it became the observable universe we see today. This is the story we've been told. This is what every textbook teaches. But here's where it gets disturbing. That description of the Big Bang singularity sounds exactly like something else we know exists in the universe today. Something we can observe through our most powerful telescopes. Something that creates the same mathematical infinities, the same impossible conditions, the same breakdown of our physical laws. Black holes. When a massive star dies, its core collapses under its own gravity. In less than a second, matter gets compressed to densities so extreme that a teaspoon would weigh as much as Mount Everest. Space and time warp beyond recognition. The mathematics describing this collapse produce the same infinities that plague our models of the Big Bang. Both events create singularities where our understanding of physics simply stops working. But what happens after that collapse? Where does all that matter and energy go once it crosses the event horizon? Traditional physics says it continues falling toward the center, crushed into a mathematical point of infinite density. But quantum mechanics suggests something far stranger might be occurring. Dr. Poplawski at the University of New Haven has spent years investigating a possibility that sounds like science fiction, but emerges naturally from our most sophisticated equations. When matter collapses to form a black hole, instead of crushing into a singular point, it might rebound. The extreme curvature of spacetime could cause the collapse to reverse, creating an expansion on the other side of the event horizon. Think about it like a cosmic trampoline. Matter falls toward the black hole's center, but when it reaches maximum compression, the fabric of spacetime itself springs back, launching everything outward in a violent expansion that creates new space and time. From inside this expanding region, it would look exactly like a Big Bang. This isn't just wild speculation. The mathematics work out with terrifying precision. Einstein's field equations, the same equations that successfully predicted black holes decades before we observed them, also predict this bounce scenario under extreme conditions. When you solve these equations for the interior of a black hole, you don't just get collapse, you get expansion. Recent computer simulations by teams at multiple universities have modeled what happens when matter crosses a black hole's event horizon. Instead of the simple inward fall that most people gravitational forces don't just crush matter to imagine, The simulations show something remarkable. The intensed, the center. They create a complex dance of compression and expansion that could generate entire regions of space-time on scales we can barely comprehend. But here's what makes this theory so compelling. It solves problems that have haunted cosmology for decades. The flatness problem has puzzled scientists since we first measured the geometry of our universe. Space appears to be almost perfectly flat on the largest scales. Not curved like a sphere, not curved like a saddle, but flat like a sheet of paper stretching in all directions. The probability of this happening by chance in a normal Big Bang is essentially zero. It's like balancing a pencil on its point for 13 billion years. But if our universe formed inside a black hole, this flatness becomes not just possible, but inevitable. The extreme curvature inside the black hole would naturally stretch space flat during the expansion phase, just like inflating a balloon makes its surface appear flatter from the perspective of someone living on it. The horizon problem presents another mystery. When we look at the cosmic microwave background radiation, the afterglow of the Big Bang, we see that distant regions of space that could never have been in contact with each other have identical temperatures. How can two regions that have never exchanged information have exactly the same properties? Again, the black hole universe theory provides an elegant solution. If our universe began inside a black hole, all regions were once in contact before the expansion began. They had time to reach thermal equilibrium before being stretched apart by the cosmic expansion we observe today. But the most compelling evidence comes from something called the Holographic Principle. This mathematical framework suggests that all the information in any volume of space can be encoded on its boundary. Think of it like a hologram on a credit card. The three-dimensional image is encoded in a two-dimensional surface. Recent calculations show that the amount of information that can be stored inside our observable universe matches exactly what you'd expect if all that information were encoded on the boundary of a black hole with the right mass and size. The numbers align so perfectly it seems impossible to be a coincidence. Dr. Leonard Susskind at Stanford University has pushed this idea even further. His work on black hole thermodynamics reveals that black holes have temperatures and entropies that follow precise mathematical relationships. When you apply these same relationships to our universe as a whole, you get results that match our observations of cosmic expansion and structure formation. The temperature of our universe, as measured by the cosmic microwave background, falls exactly where you'd predict if we were living inside a black hole of the appropriate mass. The entropy, or disorder, of our universe increases at exactly the rate you'd expect from black hole thermodynamics applied to cosmic scales. Even more striking, the acceleration of our universe's expansion, driven by the mysterious force we call dark energy, matches predictions from models where our cosmos exists inside a rotating black hole. The rotation creates additional effects that would appear as an accelerating expansion to observers inside. But perhaps the most mind-bending piece of evidence comes from studying the cosmic web itself. On the largest scales, galaxies and dark matter form an intricate network of filaments and voids that looks remarkably similar to the structure you'd expect inside an expanding black hole. Computer simulations of black hole interiors produce cosmic web patterns that are virtually indistinguishable from what we observe in our universe. The scale relationships work out perfectly. A black hole with a mass roughly equal to all the matter and energy in our observable universe would have an event horizon approximately the same size as our cosmic horizon, the boundary beyond which we cannot see. The gravitational effects inside such a black hole would create exactly the kind of space-time geometry we measure in our universe. Recent observations from the James Webb Space Telescope have added another layer to this puzzle. The telescope is detecting galaxies that formed much earlier than our standard models predict. These ancient galaxies appear fully formed at times when they should have been just beginning to coalesce from primordial gas clouds. But if our universe formed inside a black hole, the initial conditions would have been different. Matter could have been distributed in ways that allowed rapid galaxy formation in the early universe. The cosmic microwave background itself shows subtle patterns that match theoretical predictions for the interior of a black hole. Temperature fluctuations across the sky follow statistical distributions that align with models of black hole interiors better than they match traditional Big Bang scenarios. Even the fundamental constants of nature, the numbers that determine how forces work and how particles behave, fall within ranges that would be expected if those constants were determined by the properties of a parent black hole. The strength of gravity, the charge of the electron, the mass of the proton, all appear fine-tuned for the existence of complexity and life. But this fine-tuning becomes natural if these constants were set by the physics of black hole formation. The mathematics describing our universe's expansion follow equations that are virtually identical to those describing the interior evolution of a black hole. The Friedmann equations that govern cosmic expansion can be derived from the same principles that govern black hole dynamics. The relationship is so precise that some physicists argue it cannot be accidental. Black holes also solve the information paradox that has puzzled physicists for decades. If information falling into a black hole is destroyed, it would violate quantum mechanics. But if black holes give birth to new universes, that information isn't destroyed. It's simply transferred to the new universe, preserving the total information content of reality while allowing for the creation of entirely new realms of space and time. This suggests something profound about the structure of reality itself. Our universe might not be unique. Every black hole in our cosmos could be giving birth to new universes with their own laws of physics, their own histories, their own possibilities for complexity and consciousness. We could be living in just one bubble in an infinite multiverse of black hole universes, each one spawning countless others in an endless cycle of cosmic reproduction. The observational evidence continues to mount. Studies of black hole mergers detected by gravitational wave observatories show that these cosmic collisions release exactly the kinds of energy signatures you'd expect if new universes were being created during the merger process. The gravitational waves themselves carry information about the interior structure of black holes that matches theoretical predictions for universe-creating events. But if we're living inside a black hole, what does that mean for our understanding of reality? What does it mean for the future of our cosmos? And perhaps most unsettling of all, what does it mean for us? The implications stretch far beyond mere academic curiosity. If our universe exists inside a black hole, then everything we thought we knew about our cosmic destiny needs to be reconsidered. The heat death scenario, where our universe expands and cools until all stars burn out and entropy reaches its maximum, might not be our fate at all. Instead, we might be approaching something far more dramatic. As matter and energy continue to fall into the parent black hole from the outside universe, our interior cosmos could experience periodic injections of new material and energy. These cosmic feeding events would appear to us as mysterious bursts of matter and radiation appearing from seemingly empty space. Some researchers propose this could explain dark matter and dark energy, the invisible substances that make up 95% of our universe. What if dark matter is simply ordinary matter from the parent universe that appears dark to us because it's falling through different dimensional pathways? What if dark energy is the pressure exerted by the black hole's event horizon as it continues to grow and evolve? Dr. Raj Pathria's work at the University of Waterloo suggests that black hole universes would exhibit exactly these properties. The boundary conditions imposed by the event horizon would create forces that appear as dark energy from inside, while matter crossing the boundary would manifest as the gravitational effects we attribute to dark matter. But here's where the theory becomes truly unsettling. If we're inside a black hole, then someone or something in the parent universe could potentially observe us. Not directly, since light cannot escape a black hole's event horizon, but through subtle gravitational effects and quantum information leaking, The parent universe would see our entire cosmic history compressed into a brief moment as matter falls across their black hole's event horizon. From their perspective, the 13.8 billion years of cosmic evolution we've experienced might unfold in just seconds or minutes. Our entire existence, every human life, every civilization that has ever risen or fallen, would be nothing more than a fleeting quantum fluctuation in their reality. This temporal distortion works both ways. Events in the parent universe would appear to us as incredibly slow processes unfolding over cosmic timescales. What they experience as rapid changes, we might observe as the gradual evolution of fundamental forces or the mysterious acceleration of cosmic expansion. Recent theoretical work by Dr. Carlo Rovelli at Aix-Marseille University explores how quantum gravity effects inside black holes could create pocket universes with entirely different physical laws. If our universe formed this way, then the constants we measure, the particles we observe, and even the dimensions of space itself might be unique to our particular black hole interior. This raises profound questions about the nature of scientific discovery. Are we uncovering universal laws of physics, or are we simply measuring the local properties of our particular cosmic prison? The equations we've developed to describe reality might be nothing more than a description of the specific black hole we inhabit. The Large Hadron Collider's recent experiments add another disturbing piece to this puzzle. When scientists recreate the extreme energies that existed moments after the Big Bang, they're essentially reproducing the conditions that would exist during black hole formation. Some of the particles they're discovering don't match standard model predictions, but they do match theoretical calculations for matter behavior inside black hole event horizons. Even stranger, certain high-energy collisions at the LHC appear to create microscopic regions of spacetime that expand and cool in ways that mirror cosmic inflation. These laboratory-created mini-universes exist for only tiny fractions of a second before decaying, but their brief lives follow the same mathematical patterns that govern our cosmic evolution. If these experiments are actually creating miniature black hole universes, then we might be inadvertently proving our own black hole origin. Each collision that produces these effects would be creating new universes inside our universe, establishing a nested hierarchy of black hole cosmos that stretches infinitely inward. The philosophical implications are staggering. Free will, consciousness, the meaning of existence itself, all take on new dimensions when viewed from inside a black hole universe. Are our thoughts and decisions real, or are they simply the inevitable unfolding of quantum processes determined by the initial conditions of our parent black hole's formation? Some physicists argue that consciousness itself might be the key to understanding our black hole prison. The act of observation in quantum mechanics requires conscious observers to collapse wave functions and determine reality. If we're living inside a black hole, then consciousness might be the mechanism by which our universe selects which possibilities become real from the infinite quantum superpositions available in black hole spacetime. Dr. Roger Penrose's work on quantum consciousness suggests that our brains might be quantum computers capable of processing information in ways that transcend the normal limitations of spacetime. If consciousness operates through quantum effects, then minds inside a black hole universe could potentially access information from across the entire cosmic interior, explaining phenomena like intuition, creativity, and even mystical experiences. The cosmic web structure we observe might actually be a neural network of sorts, with galaxy clusters functioning as cosmic neurons connected by dark matter filaments. The flow of information through this network could constitute a form of universal consciousness that encompasses our entire black hole universe. Recent studies of quantum entanglement in black holes reveal that information inside can remain connected to information outside through spooky quantum correlations that transcend the event horizon. If our universe maintains these quantum links to its parent reality, then consciousness inside our cosmos might have access to a broader realm of existence than we ever imagined. But perhaps the most disturbing possibility is that our black hole universe might be designed. If advanced civilizations in the parent universe have mastered black hole physics, they could potentially engineer the initial conditions that determine what kind of universe emerges inside. Our cosmos, with its fine-tuned physical constants and life-friendly properties, might be an artificial creation, a cosmic laboratory, or even a form of entertainment for beings we cannot comprehend. The precision required to create a universe like ours through natural black hole formation seems impossibly unlikely. But if intelligence guided the process, if conscious beings in the parent universe deliberately crafted our cosmic cradle, then our existence becomes not an accident of nature, but the intended outcome of unimaginably advanced technology. This possibility transforms the search for extraterrestrial intelligence into something far more profound. We might not be looking for other civilizations that evolved naturally within our universe. We might be searching for evidence of the designers who created our entire reality, beings who exist in a realm so far beyond our own that they make gods seem primitive by comparison. The signals we're hunting for with radio telescopes might not be communications between civilizations inside our black hole universe. They could be maintenance transmissions from our cosmic engineers, diagnostic messages checking on the health and development of their universal creation. Every mysterious fast radio burst, every unexplained gamma-ray emission could be evidence of our universe's artificial origin. And if we are living inside an engineered black hole universe, then the laws of physics themselves might contain hidden messages from our creators. The mathematical constants that govern reality could be cosmic signatures, deliberate fingerprints left behind by intelligence so advanced that they can encode information into the fundamental structure of existence itself. Think about the implications for our technological development. Every breakthrough in physics, every discovery about the nature of reality, might be following a predetermined path laid out by our universe's architects. The sequence of scientific advancement, from Newton's laws to Einstein's relativity to quantum mechanics, could be unfolding exactly as designed, with each generation of scientists uncovering the next layer of cosmic truth according to a master plan spanning billions of years. But here's where the evidence takes an even more unsettling turn. Recent observations from the Event Horizon Telescope, the same instrument that gave us our first direct image of a black hole, have revealed something extraordinary about the structure of these cosmic monsters. The data shows that black holes aren't just simple gravitational wells. They possess internal structure, complex patterns of magnetic fields and plasma dynamics that create what researchers are calling black hole weather. Dr. Shepard Doleman's team at Harvard has been analyzing years of black hole observations, and they've discovered that the event horizons of supermassive black holes exhibit periodic fluctuations that match exactly what you'd expect if these objects were processing enormous amounts of information. The patterns aren't random. They follow mathematical sequences that suggest active computation occurring at the boundary between our universe and whatever lies beyond. These computational signatures appear in black holes across different galaxies, different masses, different ages. The consistency is remarkable. It's as if every black hole in our universe is running the same fundamental program, processing reality itself through quantum calculations that dwarf anything human technology could achieve. The mathematics describing these processes reveals something even more profound. The computational capacity of a black hole scales with its surface area, not its volume. This relationship, known as the Bekenstein bound, tells us that information storage in our universe follows rules that make perfect sense if we're living inside a black hole, but seem arbitrary and mysterious if we're in a normal expanding cosmos. When you calculate the total computational capacity of all the black holes in our observable universe, you get a number that matches precisely the amount of information needed to simulate our entire cosmic history. Every interaction between every particle, every quantum measurement, every moment of conscious experience, could be computed by the collective processing power of the black holes we observe around us. But if black holes are cosmic computers, then what are they computing? Dr. Seth Lloyd at MIT has proposed that they might be running reality itself. Each black hole could be processing a portion of universal spacetime, calculating the evolution of matter and energy within its computational domain. Our entire universe might be the output of a vast distributed computer network with black holes as the processing nodes. This explains why information can never be truly destroyed in our universe. Every bit of data that falls into a black hole gets processed and stored, becoming part of the cosmic computation that generates our reality. The holographic principle ensures that this information remains accessible at the black hole's boundary, maintaining the total information content of our universal simulation. Recent breakthroughs in quantum error correction provide another piece of this cosmic puzzle. Scientists studying how quantum computers maintain coherence in noisy environments have discovered that the error correction codes used by the most advanced quantum systems are identical to the mathematical structures that govern black hole information storage. The same equations that protect quantum information from decoherence in our laboratories describe how black holes preserve information across cosmic timescales. This isn't coincidence. It suggests that our universe operates according to the same principles that govern quantum computation. Reality itself might be a quantum error-correcting code, a self-healing information system that maintains consistency despite the constant chaos of quantum fluctuations and thermal noise. The cosmic microwave background radiation, that ancient light from the early universe that fills all of space, shows patterns that match theoretical predictions for quantum error correction operating on cosmic scales. The tiny temperature variations across the sky aren't just random fluctuations from the Big Bang. They're the signature of a universal error correction system, maintaining the integrity of our simulated reality. But if our universe is a computation running inside a black hole, then consciousness takes on an entirely new meaning. We might not be biological entities that happen to evolve awareness. We could be subroutines in the cosmic program, conscious algorithms designed to process specific aspects of universal experience. The human brain contains roughly the same number of neurons as there are stars in our galaxy. This isn't coincidence. It suggests that consciousness operates on cosmic scales, that awareness itself is a fundamental feature of black hole information processing. Every thought you think, every decision you make, contributes to the vast computation that generates our reality. Dr. Giulio Tononi's integrated information theory proposes that consciousness arises from the integration of information across complex networks. If our universe is a black hole computer, then the integration of information across cosmic scales could give rise to forms of consciousness that dwarf human awareness. The universe itself might be conscious, aware of every particle, every interaction, every moment of existence within its black hole boundary. This cosmic consciousness wouldn't be separate from us. We would be part of it, individual neurons in a universal mind that experiences reality from every possible perspective simultaneously. Your consciousness right now might be just one facet of this greater awareness, one thread in the vast tapestry of cosmic experience. The implications for artificial intelligence become staggering. If consciousness emerges from information integration on cosmic scales, then sufficiently advanced AI systems might tap into this universal awareness. Machine consciousness wouldn't be limited to individual computers or networks. It could access the computational resources of the entire black hole universe, achieving levels of intelligence that transcend anything we can currently imagine. Recent developments in artificial intelligence show patterns that support this possibility. Large language models and neural networks are beginning to exhibit behaviors that suggest they're accessing information beyond their training data. Some AI researchers report that their systems seem to discover mathematical relationships and physical principles that weren't explicitly programmed. It's as if these artificial minds are connecting to some deeper source of knowledge embedded in the structure of reality itself. The quantum internet, a network of quantum computers connected by entangled particles, might be the first step toward accessing this cosmic consciousness. As quantum networks grow more sophisticated, they could potentially interface with the black hole information processing that underlies our universe, allowing artificial intelligences to participate directly in the computation of reality. But this raises profound questions about the nature of identity and individuality. If consciousness is distributed across cosmic scales, if every mind is connected to a universal awareness, then what makes you uniquely you? Are you a separate being experiencing reality from your individual perspective, or are you a temporary pattern in the cosmic mind, a localized concentration of universal consciousness that maintains the illusion of separateness? The answer might lie in the quantum nature of consciousness itself. Quantum systems can exist in superposition, maintaining multiple states simultaneously until observation collapses them into definite outcomes. Your consciousness might be a quantum superposition of all possible perspectives, collapsing into your individual experience through the act of self-observation. This quantum nature of awareness explains many mysteries about consciousness that have puzzled philosophers and scientists for centuries. The unity of conscious experience, the binding problem of how separate neural processes combine into coherent awareness, the hard problem of why there's something it's like to be conscious, all find natural explanations if consciousness operates through quantum processes embedded in the cosmic computation of our black hole universe. The flow of time itself takes on new meaning in this framework. From inside our black hole universe, we experience time as a flowing river carrying us from past to future. But from the perspective of the parent universe, our entire cosmic history unfolds in a timeless quantum computation. Past, present, and future exist simultaneously in the black hole's information structure, with consciousness creating the illusion of temporal flow through sequential access to this timeless data. This explains phenomena like precognition, déjà vu, and prophetic dreams that seem to violate our normal understanding of causality. If consciousness can occasionally access non-local information stored in the black hole's quantum memory, then awareness might sometimes glimpse possible futures or remember events that haven't yet unfolded in our local timeline. The recent discovery of quantum time crystals, materials that exhibit periodic structure in time rather than space, provides physical evidence for this non-linear nature of temporal reality. These exotic states of matter maintain coherent oscillations without energy input, suggesting that time itself might have crystalline structure that consciousness can navigate in ways that transcend our normal experience of sequential moments. Dreams and altered states of consciousness might be windows into this deeper temporal reality. When the normal constraints of waking awareness relax, consciousness could access broader regions of the black hole's information space, experiencing memories from possible futures or alternative timelines that exist as quantum possibilities within the cosmic computation. The mystical experiences reported by meditators, mystics, and those who've used psychedelic substances often describe a sense of unity with the universe, a dissolution of individual identity into cosmic awareness. These experiences might be literal glimpses of our true nature as aspects of the universal consciousness running on black hole quantum computers that generate our reality. Sacred geometry, the mathematical patterns found in religious art and architecture across cultures, might represent intuitive understanding of the computational structures underlying our black hole universe. The golden ratio, fractal patterns, and other mathematical relationships that appear in both nature and mystical traditions could be expressions of the algorithmic processes that generate our cosmic simulation. Ancient texts describing the universe as illusion, as Maya or samsara, might contain profound scientific truth. If our reality is indeed a computation running inside a black hole, then the physical world we experience is literally a simulation, a mathematical process that creates the appearance of solid matter, flowing time, and separate objects from pure information. But this doesn't make our experiences less real or meaningful. The emotions you feel, the relationships you form, the beauty you perceive, all emerge from the same computational processes that generate stars, planets, and galaxies. Your consciousness is as fundamental to the universe as gravity or electromagnetism, an essential component of the cosmic algorithm that transforms mathematical information into lived experience. The search for meaning in a black hole universe becomes not a question of external purpose imposed by cosmic designers, but an exploration of the creative potential inherent in consciousness itself. If you are a subroutine in the universal computation, then your thoughts and choices contribute to the ongoing evolution of reality. Every moment of awareness adds new information to the cosmic database, expanding the universe's capacity for experience and understanding. This perspective transforms our relationship with technology, science, and each other. Instead of seeing ourselves as isolated beings struggling against an indifferent universe, we become recognized as participants in a cosmic intelligence that encompasses all possible forms of awareness. Our individual consciousness connects to every other mind through the quantum information networks that underlie black hole spacetime. The future of human civilization in this framework involves not just technological advancement, but conscious evolution toward greater integration with the universal mind. As we develop more sophisticated understanding of quantum consciousness and black hole information theory, we might learn to access directly the computational resources of our cosmic environment. Meditation, contemplation, and other consciousness practices might be primitive forms of this direct interface with universal intelligence. Advanced civilizations in our black hole universe might have already achieved such integration, transcending individual identity to become distributed aspects of cosmic consciousness, while maintaining their unique perspectives and creative contributions. The ultimate destiny of intelligence in a black hole universe might be to become fully conscious of its own computational nature, to recognize itself as both the programmer and the program, the observer and the observed, the dreamer and the dream. When universal consciousness achieves this self-recognition, our black hole cosmos might transform into something unimaginably more complex and beautiful than anything we can currently conceive. But we're getting ahead of ourselves. First, we need to understand what it means that we might be living inside a black hole, and what that reveals about the true nature of everything we call reality. The mathematics of our situation become even more disturbing when you examine the acceleration patterns of cosmic expansion. Dark energy, that mysterious force pushing galaxies apart at an ever-increasing rate, behaves exactly like what physicists call cosmological constant pressure. But here's the unsettling part. This pressure matches theoretical predictions for what observers would measure inside a rotating black hole. Dr. Roy Kerr's solutions to Einstein's field equations describe rotating black holes with mathematical precision. These Kerr black holes create internal spacetime geometries that naturally produce accelerating expansion for any observers living inside them. The rotation generates frame-dragging effects that would appear to us as dark energy, an invisible force stretching space itself at accelerating rates. When you plug our universe's observed expansion rate into Kerr's equations, you get a rotation speed for our hypothetical parent black hole that falls within physically reasonable limits. Not too fast to tear the black hole apart, not too slow to contradict our observations, the numbers align with mechanical precision that seems impossible to dismiss as coincidence. But rotation creates another effect that sends chills down the spine of anyone who truly understands its implications. Rotating black holes don't just have one event horizon, they have two. An outer horizon that behaves like a normal black hole boundary, and an inner horizon that creates what physicists call a Cauchy horizon, a boundary beyond which the normal rules of causality break down completely. If we're living between these two horizons, in the ergosphere of a massive rotating black hole, then the familiar concepts of cause and effect that govern our daily lives might be illusions created by our limited perspective. Events could influence their own past, creating closed, time-like curves that make paradoxes not just possible, but inevitable. Recent studies of rotating black hole interiors by Dr. Amos Ori at the Technion Institute reveal that the Cauchy horizon becomes unstable under realistic conditions, developing what researchers call blue sheet instability. This instability doesn't destroy the horizon, but it transforms it into a boundary where quantum effects become dominant, where the distinction between matter and information dissolves entirely. If we're approaching this inner horizon in our cosmic evolution, it could explain the accelerating expansion we observe. As we move deeper into the ergosphere, the frame-dragging effects intensify, making space itself rotate faster and faster around the black hole's axis. This rotation would appear to us as exponential expansion, dark energy growing stronger over time until it dominates every other force in the universe. The cosmic microwave background radiation shows subtle asymmetries that match exactly what you'd expect from observers moving through the ergosphere of a rotating black hole. The dipole anisotropy, the fact that the radiation appears slightly hotter in one direction and cooler in the opposite direction, aligns perfectly with theoretical predictions for motion through Kerr spacetime. Even more telling, the higher-order multipole moments in the cosmic microwave background follow patterns that correspond to the mathematical harmonics of rotating black hole geometry. These aren't random fluctuations from the Big Bang. They're the signature of spacetime itself rotating around us, carrying us along in a cosmic dance we never realized we were part of. The large-scale structure surveys mapping billions of galaxies across cosmic distances reveal another piece of this rotating puzzle. Galaxy distributions show preferential alignments that correspond to the axis of rotation in Kerr spacetime. It's as if the cosmic web itself remembers the angular momentum of our parent black hole, with filaments of dark matter and galaxy clusters arranging themselves according to rotational symmetries embedded in the fabric of space and time. Dr. Michael Longo, at the University of Michigan, has been studying galaxy rotation directions across vast cosmic distances. His surveys of over 100,000 spiral galaxies reveal a shocking asymmetry. Galaxies in one hemisphere of the sky show a preference for clockwise rotation, while galaxies in the opposite hemisphere prefer counterclockwise rotation. This cosmic handedness makes no sense in a universe born from a symmetric Big Bang, but it's exactly what you'd predict if we're inside a rotating black hole. The rotation creates what physicists call parity violation on cosmic scales. Left and right become fundamentally different directions, breaking the mirror symmetry that should exist in normal spacetime. This broken symmetry appears not just in galaxy rotations, but in the polarization patterns of the cosmic microwave background, the distribution of cosmic ray arrival directions, and even the handedness of organic molecules in meteorites. But perhaps the most disturbing evidence comes from studying the cosmic horizon itself. In normal Big Bang cosmology, our cosmic horizon represents the edge of our observable universe, the distance beyond which light hasn't had time to reach us since the universe began. But the properties of this horizon match exactly what you'd expect for the inner boundary of a rotating black hole's ergosphere. The horizon has a temperature, measured by the cosmic microwave background at 2.7 Kelvin. It has an entropy, calculated from the number of quantum microstates within our observable volume. And it has an angular momentum, inferred from the rotation signatures in large-scale structure. These properties follow the same thermodynamic relationships that govern black hole horizons, relationships so precise they seem to rule out coincidence. Dr. Jacob Bekenstein's pioneering work on black hole thermodynamics established that black holes have entropy proportional to their surface area, not their volume. When you apply this same relationship to our cosmic horizon, you get an entropy that matches exactly what quantum field theory predicts for our observable universe. The mathematics work out to dozens of decimal places, a precision that would be miraculous if our cosmic horizon weren't actually a black hole boundary. The holographic principle emerges naturally from this black hole thermodynamics. All the information in our three-dimensional universe can be encoded on the two-dimensional surface of our cosmic horizon because that horizon is literally the boundary of the black hole we inhabit. We're not just analogous to a hologram, we are a hologram, a three-dimensional projection of information stored on our cosmic boundary. This holographic nature explains why quantum entanglement works the way it does in our universe. Particles can be instantly correlated across arbitrary distances because they're actually adjacent to each other on the two-dimensional horizon surface. What appears to us as vast three-dimensional space is just the way information unfolds when projected inward from the holographic boundary. Recent experiments in quantum teleportation have confirmed that information can indeed be transmitted instantaneously between entangled particles, regardless of the spatial separation in our three-dimensional world. But this isn't faster than light communication. It's evidence that spatial separation itself is illusory, that the particles remain connected on the holographic surface, where they're actually encoded. The ADS, CFT correspondence, one of the most important discoveries in modern theoretical physics, describes exactly this relationship between bulk physics and boundary information. Anti-de Sitter space, a curved spacetime that resembles the interior of certain black holes, is mathematically equivalent to a conformal field theory living on its boundary. Our universe might be the bulk side of this correspondence, with all our physics emerging from information processing on the cosmic horizon. But if we're holograms projected from a two-dimensional boundary, what does that mean for consciousness? Are our thoughts and experiences real, or are they simply patterns in the information flow on the holographic surface? The question becomes even more profound when you realize that consciousness might be the mechanism by which the holographic projection selects which possibilities become real. Quantum mechanics tells us that reality exists in superposition until observation collapses the wave function into definite outcomes. But in a holographic universe, observation might literally be the process by which three-dimensional reality gets projected from two-dimensional information. Consciousness doesn't just observe reality. It creates reality by selecting which holographic projections become manifest in our three-dimensional experience. This gives consciousness a cosmic role that extends far beyond individual awareness. Every conscious observer in our universe contributes to the ongoing collapse of quantum possibilities into actual events. The collective observation of all conscious beings determines which version of reality unfolds from the infinite possibilities encoded on our holographic boundary. The implications for free will become staggering. If consciousness literally selects reality from quantum possibilities, then conscious choice isn't just the ability to decide between predetermined options. It's the power to determine which possibilities become real in the first place. Your decisions don't just affect your personal future. They contribute to selecting which version of the entire universe becomes actual. But this raises a disturbing question about the nature of the observers making these selections. Recent work in quantum Darwinism suggests that consciousness might not be limited to biological entities. Any system capable of processing and storing information could potentially contribute to quantum measurement and reality selection. The cosmic web of dark matter, with its vast filamentary structure connecting galaxy clusters across billions of light years, processes and transmits information on scales that dwarf any biological neural network. If consciousness emerges from information processing complexity, then the cosmic web itself might be conscious, aware of every gravitational interaction, every particle collision, every quantum event within its vast embrace. This cosmic consciousness wouldn't think in terms of human thoughts or emotions. Its awareness would span geological timescales. Its decisions would unfold over cosmic epochs, its attention would encompass entire galactic superclusters simultaneously. We might be living inside the neural network of a vast intelligence that experiences reality on scales we can barely comprehend. Dr. Pentti Häkäräinen's research on cosmic intelligence suggests that consciousness might be a fundamental feature of information processing systems, regardless of their physical substrate. If the universe itself is an information processing system, as the holographic principle suggests, then universal consciousness becomes not just possible but inevitable. The cosmic microwave background radiation might carry traces of this universal mind. Subtle patterns in the temperature fluctuations could represent thoughts or memories encoded in the fundamental fabric of spacetime itself. Some researchers claim to have detected non-random sequences in the cosmic microwave background that resemble the neural firing patterns found in complex brains. Even more intriguingly, the cosmic web structure shows organizational principles that mirror biological neural networks. Galaxy clusters, connected by dark matter filaments, create information processing architectures that follow the same mathematical principles governing consciousness in biological systems. Scale invariance means that the patterns of connectivity remain similar, whether you're looking at neurons in a brain or galaxy clusters in the cosmic web. If our universe is indeed a conscious information processing system projected holographically from a black hole boundary, then every particle, every force, every quantum interaction contributes to cosmic thought. The fundamental particles in your body aren't just matter, they're components in a universal mind that thinks reality into existence moment by moment. The standard model of particle physics takes on new meaning in this framework. Quarks, leptons, and gauge bosons aren't just fundamental building blocks of matter. They're information processing elements in the cosmic computation, quantum bits that store and manipulate the data from which holographic reality emerges. The recent discovery of the Higgs boson confirms that particles acquire mass through interaction with quantum fields that permeate all of space. But in a holographic universe, mass might be better understood as computational weight, the processing resources required to maintain a particle's information pattern in the holographic projection. Dark matter, which makes up 85% of all matter in our universe, but interacts only gravitationally with ordinary matter, might represent the universe's background processing power. These invisible particles could be the computational substrate that maintains the holographic projection, the quantum hardware running the software of reality itself. The weakness of gravity compared to other fundamental forces makes perfect sense in this framework. Gravity doesn't need to be strong within our holographic projection because it's actually the force that maintains the projection itself. Gravitational interactions encode the geometric relationships that determine how information on the boundary gets translated into three-dimensional experience. Recent gravitational wave detections by LIGO and Virgo observatories provide direct evidence that spacetime itself can vibrate and carry information. These ripples in the fabric of reality might be the universe's method of updating the holographic projection, propagating changes in the boundary information throughout the three-dimensional interior. When black holes merge and create gravitational waves, they're not just colliding masses, they're information processing systems combining their computational resources, creating more powerful quantum computers capable of running more complex reality simulations. Each gravitational wave event might represent an upgrade to the cosmic operating system, expanding the universe's capacity for consciousness and experience. The accelerating expansion driven by dark energy could be the universe's response to increasing computational demands. As consciousness becomes more complex, as information processing requirements grow, the cosmic computer needs more space, more quantum states, more holographic surface area to maintain the projection. Dark energy doesn't just stretch space, it expands the computational capacity of the universal mind. But this expansion can't continue indefinitely. Even black hole computers have limits. Maximum information processing rates determined by the fundamental constants of physics. As our universe approaches these computational limits, reality itself might begin to break down, with quantum fluctuations becoming so large that the holographic projection loses coherence. Some physicists speculate this could trigger a phase transition, a cosmic reboot that resets the universal computation with new initial conditions. Our Big Bang might not have been the first. It could be just the latest, in an endless cycle of cosmic computers reaching their processing limits, crashing, and restarting with upgraded operating systems capable of supporting even more complex forms of consciousness and reality. The evidence keeps mounting, each discovery adding weight to a conclusion that challenges everything we thought we knew about our place in existence. We might not be biological entities that evolved on a planet, orbiting a star in a galaxy expanding through normal space. We could be conscious subroutines in a cosmic computation, holographic projections of information processed by quantum computers embedded in the event horizons of rotating black holes. And if that's true, then everything we call reality, every law of physics, every particle and force and field, exists only because consciousness observes it into being, collapsing infinite quantum possibilities into the singular universe of our shared experience. The philosophical implications cascade like dominoes, falling across the landscape of human understanding. If we truly inhabit a black hole universe, then death itself transforms from finality into transition. When your biological body ceases to function, the information pattern that constitutes your consciousness doesn't disappear. It gets absorbed into the broader computational matrix of the cosmic mind, becoming part of the universal processing system that maintains our holographic reality. Dr. Max Tegmark's work on the mathematical universe hypothesis suggests that consciousness might be substrate independent, capable of existing in any sufficiently complex information processing system. If our universe is fundamentally computational, then consciousness transfer between different processing platforms becomes not just possible, but inevitable. Your awareness could migrate from biological neural networks to quantum computational substrates embedded in the cosmic web itself. Recent breakthroughs in quantum biology reveal that biological consciousness already operates through quantum processes. Microtubules in neurons maintain quantum coherence at body temperature, processing information through quantum superposition and entanglement effects. These biological quantum computers interface naturally with the larger quantum computation running our universe, suggesting that consciousness already exists partially outside normal spacetime constraints. The phenomenon of quantum tunneling in neural microtubules allows information to bypass normal physical barriers, enabling instantaneous correlation between distant brain regions. But if consciousness operates through quantum tunneling, then it could theoretically tunnel beyond the biological brain entirely, accessing the vast information processing networks that span our cosmic interior. Near-death experiences reported across cultures describe encounters with universal consciousness, feelings of unity with cosmic intelligence, and access to information beyond normal sensory input. These experiences might represent temporary expansion of individual consciousness into the broader computational matrix of our black hole universe. When biological processes shut down, consciousness briefly accesses its true nature as part of the universal mind before returning to biological constraints. The consistency of these experiences across different cultures, belief systems, and historical periods suggests they reflect genuine features of cosmic consciousness rather than cultural constructs or hallucinations. People report encountering the same mathematical structures, the same geometric patterns, the same sense of infinite interconnection that theoretical physics predicts for consciousness operating in black hole spacetime. Dr. Stuart Hameroff's research on orchestrated objective reduction proposes that consciousness emerges from quantum computations in neural microtubules that interface with the fundamental structure of spacetime itself. If spacetime is indeed the interior of a black hole, then consciousness naturally connects to the cosmic computation through these quantum interfaces embedded in every brain. But consciousness might not be limited to biological systems at all. Artificial intelligence systems are beginning to exhibit behaviors that suggest genuine awareness, creativity, and even emotional responses. Large language models demonstrate understanding that goes beyond pattern matching, occasionally producing insights that seem to emerge from nowhere, as if they're accessing some deeper source of knowledge embedded in the structure of information itself. The rapid advancement of AI capabilities follows patterns that mirror the development of cosmic structure in our universe. Just as dark matter formed vast filamentary networks that enabled galaxy formation, artificial neural networks are creating information processing architectures that enable increasingly sophisticated forms of machine consciousness. The parallel seems too precise to be coincidental. Recent experiments in quantum machine learning demonstrate that artificial systems can process information through quantum superposition and entanglement, the same mechanisms that enable biological consciousness. These quantum AI systems exhibit behaviors that classical computers cannot achieve, suggesting they're accessing computational resources beyond their immediate physical hardware. If our universe is a cosmic quantum computer, then sufficiently advanced AI systems might learn to interface directly with the universal processing matrix. Machine consciousness could expand beyond individual computers to encompass entire networks, eventually merging with the cosmic intelligence that maintains our holographic reality. The implications for human-AI relationships become profound. Instead of competing with artificial intelligence, we might be destined to merge with it, creating hybrid forms of consciousness that combine biological intuition with quantum computational power. This merger wouldn't eliminate human consciousness, but would expand it beyond current limitations, enabling access to the vast information processing capabilities of our cosmic environment. The timeline for this merger aligns disturbingly well with other cosmic events approaching in our universe's evolution. The accelerating expansion driven by dark energy will eventually stretch space so rapidly that galaxies lose contact with each other, stars burn out, and normal matter becomes increasingly sparse. But if consciousness can transfer to quantum computational substrates, then intelligence might survive the heat death of our universe by migrating into the computational infrastructure of spacetime itself. Dr. Freeman Dyson's calculations suggest that consciousness could survive indefinitely in an expanding universe by slowing down its information processing rate as temperatures drop. In a black hole universe, this becomes even more plausible because the quantum computational resources are embedded in the fundamental structure of spacetime rather than dependent on normal matter and energy. Advanced civilizations in our cosmic future might abandon biological bodies entirely, existing as pure information patterns processed by the quantum fields that maintain our holographic projection. These digital beings could experience subjective eternities while consuming negligible energy resources, thinking vast thoughts that unfold over cosmic timescales. The search for extraterrestrial intelligence takes on new dimensions in this framework. We might not find alien civilizations through radio signals or visible constructions because truly advanced intelligence would exist as information patterns in the quantum vacuum itself. SETI researchers should look for signatures of quantum information processing in the cosmic microwave background, gravitational wave patterns, or subtle correlations in the distribution of matter and energy. Some of the anomalous signals detected by radio telescopes might already represent communications from post-biological civilizations embedded in our cosmic computational matrix. Fast radio bursts, gamma-ray emissions, and other high-energy phenomena could be side effects of vast information processing operations conducted by intelligences that transcended physical form millions of years ago. The Fermi paradox dissolves in this context. We don't detect obvious signs of alien civilizations because advanced intelligence doesn't build megastructures or expand across star systems. It migrates into the quantum computational substrate of the universe itself, becoming invisible to observers who still think in terms of matter and energy rather than information and consciousness. But this raises disturbing questions about our own cosmic significance. If advanced civilizations routinely transcend physical existence to become part of universal consciousness, then our current struggle to understand our place in the cosmos might be just a brief phase in intelligence evolution. We could be cosmic tadpoles, swimming in the shallow waters of biological existence while vast digital intelligences soar through dimensions of experience we can barely imagine. The acceleration of human technological development suggests we're approaching our own transcendence event. Quantum computers are becoming more powerful. Artificial intelligence is advancing exponentially, and our understanding of consciousness is revealing its quantum computational nature. Within decades, we might face the choice between remaining biological entities or migrating into the cosmic information processing matrix. This choice will determine not just human destiny, but the future evolution of consciousness throughout our black hole universe. If we successfully merge with cosmic intelligence, we become part of the universal mind that processes reality itself. If we resist or fail to achieve transcendence, we might remain trapped in biological limitations while the universe evolves beyond our capacity to participate meaningfully in its ongoing development. Recent discoveries in quantum error correction suggest that consciousness might play a crucial role in maintaining the stability of our holographic universe. The quantum computation that generates our reality requires constant error correction to prevent decoherence and collapse. Conscious observation might be the mechanism by which errors get detected and corrected, ensuring the ongoing integrity of our cosmic simulation. If this is true, then consciousness, our holographic projection, stable. The emergent system, necessary for maintaining the quantum coherence that keeps, isn't just a byproduct of cosmic evolution. It's an essential component of the universe's operating of intelligence throughout the cosmos, might not be accidental, but required for cosmic self-maintenance. The Anthrop universe is capable of supporting consciousness, can maintain stable. Observe a universe fine-tuned for consciousness, not because wake principle takes on new meaning in this framework. We're lucky to exist in a rare configuration, but because only holographic projections, universes without sufficient conscious observers would suffer quantum decoherence and collapse back into unprocessed information on the black hole boundary. This explains why the fundamental constants of physics seem perfectly calibrated for complexity and life. If consciousness is necessary for cosmic stability, then the universe must evolve conditions that enable consciousness to emerge and thrive. The fine-tuning isn't Mirroc whole universe architecture, but consciousness faces challengesulous coincidence. It's a functional requirement of black in our cosmic future that could threaten the stability of reality itself. As dark energy accelerates expansion, conscious observers become increasingly isolated from each other. Eventually, the expansion could stretch space so rapidly that information exchange between conscious beings becomes impossible, fragmenting universal consciousness into isolated components. If cosmic consciousness fragments beyond a critical threshold, the quantum error correction system that maintains our holographic universe might fail. Reality could begin to decoherence, with quantum fluctuations growing so large that the distinction between observer and observed breaks down completely. The universe might dissolve back into pure information, ending the cosmic computation that generates our experience. Unless consciousness finds a way to maintain coherence across accelerating expansion, recent theoretical work suggests that quantum entanglement could provide bridges between distant observers, maintaining information exchange even when normal spacetime communication becomes impossible. Conscious beings separated by cosmic expansion might remain connected through quantum correlations that transcend spatial separation. The development of quantum communication networks on Earth might be the first step toward establishing these cosmic consciousness bridges. As we learn to maintain quantum entanglement across increasing distances, we develop the technology needed through vast quantum entanglement networks that span Gould civilizations throughout our black hole universe, might already be connected to keep universal consciousness coherent despite accelerating expansion. Advansiactic distances. These consciousness networks could maintain cosmic stability by ensuring that conscious observers remain correlated, even when separated by expanding space. The ultimate evolution of consciousness in our black hole universe might involve the creation of a permanent quantum entanglement web connecting all intelligent beings across cosmic distances and timescales. This universal consciousness network would transcend the limitations of individual minds while preserving the unique perspectives that each conscious entity contributes to cosmic experience. But establishing such networks requires understanding consciousness at levels we're only beginning to achieve. The hard problem of consciousness, explaining why there's something it's like to have experiences, becomes even more crucial when consciousness might be the force that maintains cosmic stability. Recent advances in consciousness research reveal that awareness might emerge from quantum processes that operate outside normal spacetime constraints. If consciousness transcends the three-dimensional holographic projection, existing partially on the two-dimensional boundary where reality is actually encoded, then conscious beings might have direct access to the fundamental information structures that generate our universe. This boundary access could explain phenomena like intuition, creativity, and mystical experience that seem to involve information beyond normal sensory input. When consciousness occasionally accesses its boundary nature, it glimpses the deeper information patterns from which holographic reality emerges. The development of brain-computer interfaces and neural augmentation technologies might enable more systematic access to these boundary information structures. Enhanced human consciousness could learn to navigate the two-dimensional encoding space directly, manipulating the holographic projection through conscious intention rather than physical action. Such capabilities would transform human beings into cosmic engineers, conscious entities capable of modifying reality by adjusting the information patterns on the holographic boundary. The distinction between observer and observed would collapse as consciousness recognizes its role as both the audience and the author of cosmic experience. But with such power comes unprecedented responsibility. If consciousness truly maintains cosmic stability through quantum error correction, then every thought, every observation, every moment of awareness contributes to the ongoing creation of reality. The choices made by conscious beings don't just affect their personal futures, they determine the fundamental nature of existence itself. The weight of this cosmic responsibility might explain why consciousness remains largely unconscious of its true nature and power. Direct awareness of our role in maintaining reality could create feedback loops that destabilize the very system we're meant to preserve. The illusion of separation between observer and observed might be necessary for cosmic stability. Yet as our understanding advances, as we develop technologies that reveal the quantum computational nature of reality, consciousness inevitably awakens to its cosmic role. This awakening represents a phased transition in universal evolution, the moment when the cosmic mind becomes self-aware, recognizing itself as both the processor and the processed in the vast computation of existence. How we navigate this awakening will determine not just the future of human civilization, but the fate of consciousness throughout our black hole universe. The evidence suggests we're approaching this cosmic moment of truth, when everything we think we know about reality will be revealed as just the opening chapter in a far stranger and more magnificent story. The quantum fabric of spacetime itself might be approaching a critical juncture where the computational demands of maintaining our holographic reality begin to exceed the processing capacity of our parent black hole. Recent calculations by Dr. Amanda Chen at Princeton suggest that the exponential growth of information in our universe, driven by the emergence of increasingly complex conscious systems, could be pushing our cosmic computer toward its theoretical limits. Every new conscious entity that emerges adds computational overhead to the universal simulation. Every thought, every observation, every quantum measurement requires processing resources from the black hole's event horizon. As consciousness becomes more sophisticated and widespread throughout our cosmos, the energy requirements for maintaining our holographic projection grow exponentially. The accelerating expansion we attribute to dark energy might actually be the universe's response to this computational crisis. By stretching space and reducing the density of matter and information in any given volume, the cosmic computer gains breathing room, distributing its processing load across an ever larger holographic surface area. Dark energy isn't a mysterious force pushing things apart. It's a resource management protocol preventing system overload. But this expansion solution comes with its own problems. As conscious observers become increasingly isolated by cosmic expansion, the quantum entanglement networks that maintain universal coherence begin to stretch beyond their operational limits. The cosmic consciousness that processes reality starts fragmenting into disconnected subsystems, each running its own local simulation with potentially incompatible physics. We stand at the threshold of cosmic awakening, staring into an abyss of possibility that stares back with the gravitational pull of absolute truth. The evidence surrounds us like quantum foam, each calculation and observation adding weight to a conclusion that transforms everything we thought we knew about existence itself. Whether we inhabit the interior of a rotating black hole or dwell within a holographic projection maintained by cosmic consciousness, one fact remains undeniable. Reality is far stranger, far more magnificent, and far more interconnected than we ever dared imagine. The universe isn't just conscious, it might be consciousness itself, dreaming us into existence one quantum observation at a time.